Hello, welcome to Lecture 2 of my course on the mathematics of lattice-based cryptography. In this lecture, I'll introduce the short integer solutions, or SIS problem, which is a computational problem which is necessary for the security of several lattice-based cryptographic schemes. In Lecture 5, we'll see the relationship between SIS and lattices. Let me remind you that the lecture slides are available on my course webpage, cryptography101.ca. Okay, here's some notation I'll use in the course. The set of integers modulo q, denoted zq, is comprised of the integers between 0 and q minus 1, and where addition, subtraction, and multiplication are performed modulo q. I'll use this notation for the selection of x, uniformly and independently at random from the set S. All vectors are column vectors. The short integer solutions problem, SIS, was introduced by Itai in his landmark 1996 paper. The problem has four parameters, n, m, q, and b. Q is a prime number, and b is the error bound. The SIS problem is the following. Given an n by m matrix whose entries are randomly selected from the integers modulo q, find a non-zero solution z to the matrix equation az equals 0 modulo q, where the components zi of the vector z are integers between minus b and b. Here the error bound b is quite a bit smaller than q over 2. Note that such a vector z is in the null space of the matrix A modulo q. Of course, one can efficiently find all solutions to the matrix equation using Gaussian elimination modulo q. However, one is then faced with the challenge of identifying one of these solutions that is non-zero and small, where small means having relatively small components. The requirement that z is non-zero and has relatively small components is what makes the problem challenging. I'll remark that the components zi of an SIS solution vector z are integers between minus b and b. If these components zi are considered to be integers modulo q, then they would be between q minus b and b, as shown in the figure. This is because q minus b is congruent to minus b modulo q. I'll next make some notes about the existence of an SIS solution. If the matrix A has at least as many rows as columns, i.e. n is at least equal to m, then one expects that A has rank m over the integers modulo q. The null space of such a matrix would have dimension 0, so the only solution to az equals 0 modulo q is z equals 0. Thus, no SIS solution exists. We will henceforth assume that n is less than m. In other words, the matrix A has more columns than rows. Suppose next that b plus 1 to the power m is greater than q to the n. Consider length m vectors z, whose components are between minus b over 2 and b over 2. For simplicity, I'm assuming here that b is even. The total number of such vectors z is b plus 1 to the power m, since there are b plus 1 choices for each component of z. Now, az modulo q is a vector of length n, whose components are integers modulo q. There are q to the n such vectors. Since q to the n is less than b plus 1 to the power m, the pigeonhole principle informs us that there must exist two length m vectors, z1 and z2, whose components are between minus b over 2 and b over 2, that yield the same vector upon multiplication by a modulo q. In other words, az1 equals az2 modulo q. Then, the vector z, defined to be z1 minus z2, satisfies az equals 0 modulo q. Moreover, z is non-zero, since z1 is not equal to z2, and the components of Z are between minus B and B. Thus, Z is an SIS solution. We'll henceforth assume that b plus 1 to the power m is greater than q to the n, whereby an SIS solution is guaranteed to exist. Lastly, I'll note that the SIS solution is not unique. Indeed, if Z is an SIS solution, then so is minus Z modulo Q. And there could be other solutions. Here's an example of the SIS problem. Let's take n equals 3, m equals 5, q equals 13, and b equals 3. Here is an SIS instance. The matrix A is 3 by 5, and its entries are randomly selected integers between 0 and 12. We need to find a length 5 vector Z that is a solution to AZ equals 0 modulo 13, where Z is non-zero and has integer components between minus 3 and 3. Equivalently, the components of Z, when reduced modulo 13, should be between 0 and 3, or between 10 and 12. So working over the integers modulo 13, Gaussian elimination on A yields this reduced matrix A primed. We see that A primed has rank 3, so its null space has dimension 2. The unconstrained variables are Z4 and Z5, and the complete solution to the system of equations is Z1 equals 8Z4 plus 3Z5 from the first row of A primed, Z2 equals 3Z4 plus Z5 from the second row of A primed, and Z3 equals 12Z4 plus 12Z5 from the third row of A primed. This gives a total of 169 solutions Z. Of these, exactly 6 are SIS solutions. In other words, non-zero vectors whose integer components are between minus 3 and 3. Observe that the 6 SIS solutions come in pairs. Here's one cryptographic application of SIS, the design of a collision-resistant hash function. The hash function parameters are a randomly selected n by m matrix A with entries from the integers modulo Q. We'll assume that the number of columns m in A is greater than the number of rows n times log Q. The hash function maps binary strings of length m to length n vectors over the integers modulo Q. The binary string z is mapped to the vector a times z modulo q. The hash function is a compression function in the sense that the domain has size 2 to the m, which is greater than the size q to the n of the codomain. We have a short proof that the hash function is indeed collision resistant, assuming the hardness of SIS. Suppose by way of contradiction that one can efficiently find a collision for H. So one can efficiently find two distinct length m binary strings, Z1 and Z2, with the same hash value. So A times Z1 equals A times Z2 modulo Q, and so A times Z is 0 modulo Q, where Z is defined to be Z1 minus Z2. Now, since Z is non-zero, and its components are either minus 1, 0, or 1, Z is an SIS solution with error bound b equals 1 that we have efficiently found. This contradicts hardness of SIS. I'll next present two variants of SIS. The first is the inhomogeneous version of SIS, which has a rather unfortunate acronym, ISIS. An ISIS instance is a randomly selected n by m matrix A with entries from the integers modulo Q, and a randomly selected length m vector B with entries also from the integers modulo Q. The challenge is to find a small solution Z to the equation A times Z equals B modulo Q. Here, small as usual means that the coordinates of Z are between -b and b. Of course, it's possible that an ISIS solution doesn't exist. Let's make the heuristic assumption that multiplying A by a small length m vector z, whose entries are between -b and b, produces a random length n vector b. The number of such small vectors z is 2b plus 1 to the power m, and the number of vectors b is q to the n. So, if 2b plus 1 to the power m is much greater than q to the n, we would expect that at least one small vector z yields the target vector b. So henceforth, we'll assume that 2b plus 1 to the power m is much greater than q to the n. In other words, m is much greater than n log n divided by the log of 2b plus 1. In this event, an ISIS solution is expected to exist with very high probability. I'll now show that SIS and ISIS are equivalent. First, I'll prove that SIS reduces to ISIS. So suppose that we are given an SIS instance A. We'll show that an SIS solution can be efficiently found, assuming that we have an efficient ISIS solver. We'll call A's last column minus B primed, and the remaining columns of A yield a matrix A primed. A primed has n rows and m minus 1 columns. So A prime B primed is an instance of ISIS. We'll now use our ISIS solver to efficiently find, with non-negligible probability, a small solution Z primed that satisfies A primed times Z primed equals B primed modulo Q. You can now check that the length m vector Z, obtained by appending a 1 to the end of the length m minus 1 vector Z primed, is a solution to the given SIS instance. This proves that SIS reduces to ISIS. I'll now prove that ISIS reduces to SIS. So, suppose that we are given an ISIS instance AB. We'll show that an ISIS solution can be efficiently found, assuming that we have an efficient SIS solver. We'll begin by selecting a random index j between 1 and n plus 1, and a random non-zero integer c between -b and b. C is our guess for the jth entry of the solution to the SIS instance that we'll construct as follows. Let A primed be the matrix obtained by inserting minus C inverse times B modulo Q as a new jth column in A. Note that A primed has n rows and m plus 1 columns. We'll now use our SIS solver to efficiently find, with non-negligible probability, a small non-zero Z primed that satisfies A primed times Z primed equals 0 modulo Q. Now, if the jth entry of Z primed is indeed C, then we'll define Z to be the length m vector obtained from Z primed by deleting its jth entry. You can check that Z is an ISIS solution, so it's non-zero, has components between -b and b, and satisfies A times Z equals B modulo Q. Thus, we have efficiently found an ISIS solution, not with certainty, but with probability 1 over m times q, and this is non-negligible. This proves that ISIS reduces to SIS. And this establishes the equivalence of SIS and ISIS. A second variant of SIS is normal form ISIS. This variant differs from ISIS in that the matrix is in normal form. So the matrix is now a matrix with n rows and m plus n columns. The left portion of the matrix is a randomly selected matrix A with n rows and m columns. And the rightmost n columns of the matrix are the columns of the n by n identity matrix IN. I claim that the normal form ISIS problem with parameters n, m, q, and b is equivalent to the ISIS problem with parameters n, n plus m, q, and b. We'll first prove that normal form ISIS reduces to ISIS. So suppose we are given a normal form ISIS instance AB. We'll select a random n times n matrix C. Now, C is invertible modulo Q, with probability roughly Q minus 1 over Q. To argue this heuristically, assume that the determinant of C is a uniformly random integer modulo Q. Then, the probability that the determinant is non-zero is Q minus 1 over Q. Now, assuming that C is invertible, C times A is a uniformly random n times m matrix, and C times B is a uniformly random and independent length n vector. Thus, CAC, CB is an ISIS instance. This ISIS instance has the same solution space as a normal form ISIS instance AB. Thus, we can use the ISIS solver to efficiently find an ISIS solution with non-negligible probability. And this is also a solution to the given normal form ISIS instance, thus proving that normal form ISIS reduces to ISIS. The proof that ISIS reduces to normal form ISIS uses the same idea. I'll let you check the details for yourself.